Hi, hello. My name is Albert Shaju. So, uh, I hope that you guys understood. You guys have a basic understanding of how to uh, use the LTs for highs, at least how to take up the different components, how to assign the value, and to have a basic understanding of how the transient analysis works, how the AC analysis works, how to do these things. So uh, in this section, we are not going to have a step-by-step approach of how to design a circuit. Instead, what we are going to do is we are going to uh, look keenly on some of the extra special features that you can find in LT-Spice that makes the analysis more easier and helps in helps you in making the design of the circuit in a more efficient manner. So uh, so let's start. Okay, so you can see the head here. I have already made the circuit. So here you can pause the video, and if you would like, you can make the same circuit as such, or any kind of transient circuit would be fine. So I have used the voltage source. I have a resistor here, and in order to use current source, we need some kind of we need a voltage source in order to give reference for the current. So we have used this one, and this is a voltage control voltage source. This is a current source which in require this reference component, and then you have the resistor hers. And I have used the transient analysis here from yeah, you could have seen this one. So this is the transient analysis as that I have given this one. Okay, so we have a start time of 0 second and a stop time of 4 second with a time step of 1 millisecond. So okay, so I'm going to run this one. So through this circuit, what we are going to focus is about mainly about the graphs. What we are like some extra features that you can see in graphs. So that's what we are going to look. So I'll just run this one for you. Okay, so I can use this one. Okay, let's say what is the yeah, you can see, yeah, this is a basic there is no other capacity component. This is the basic resistive component. So you can see the hand. I gave a sine wave here. I have a sine wave here. I get an output basically sine wave. So yeah, let's see. Uh, yeah, here even here you have a sine wave. Yeah, so here you have a sine wave. So sine wave. Okay, so now, but like you can see what is this VN001, VN0005. These are really the nodes. Like what we have is the nodal voltage. So we know what is nodal analysis. So like nodes are points where here we have common voltages. So these are nodal points. So like the analysis become much easier if we are able to name them. So and LT-Spice enables to name uh, different nodes. So we look into that. Okay, so you have this label hat. Just click on it. Just click on it. Then just give a name. Let's see, I am giving it V out. V out. Click on OK. Um, just place V out wherever you want. I am putting it at the load resistance. So V out. Click on the um, right click. Give a right click so that you have your cursor back. So this is your so again I will move to come yeah, label net. Okay, let's give it v in. Click on OK. So I'll just keep it yeah, here v in. Okay, uh, then now let's run this one. So Okay. Okay, so let's see the voltage here. Now we can see the hand, it is now V out. You can see the hand, this has become V out. So has become V out. So okay, so this has become V out. Similarly, if I look the voltage here, you can see that like the name of the node has been changed to V out, voltage of V out, and this has a voltage of V in. Similarly, yeah, so this is his voltage of V out, voltage of V in, and yeah, so similarly you can name different and you can name different nodes, and yeah, like even if you try to find the voltage at this point, it will give you the same V out, because all these points have same voltages. And this is, yeah, here if you click on this one, you will get the current through ICIS. That's what this means, current through ICIS. Okay, so this is how we label this one. Now I will give some so now let's see what all things can be done inside, like in this graph. So you can see this one. So first of all, let's say let's like there are number of features that you can have in the graph. So first, let's say how to understand how to just look into different points. So now, in order to have a good idea of what this point is, just left click. So let's say, hey, we are required to analyze this V out. Let's say we are looking in what are the different points, what are the different voltages of V out. So left click on V out. Now you have this cursor here. So move this cursor when you are like moving a hand. So like it goes through the curve, and you can see on the uh, right side, you can see what are the values. So yeah, you can just move in. So similarly, if you have to look into I current and this red graph, so you just click on the hand, you can hand move through this one. Same goes for V in, and you can see the horizontal values and the vertical value over there. So okay, and in order to like let's to yeah, you can even, yeah, you can zoom. Of course, you can zoom in and zoom out if you, or you can just zoom in if you need. You can just go to zoom in and have a uh, like a better, a more accurate, precise uh, point if required. Okay, so that's about how you can move your cursor. Okay, and even you can even annotate his points. Okay, you have um, an option called draw. So there are different things you can annotate, and one thing that comes quite handy is this cursor position. So you can just click on the cursor position, and it will give the x and y coordinates of your cursor where you have placed your cursor earlier. And you can, like, there is also that edit option, in which, like, if you just right click on the this one, you can see the color option, and you can even so yeah, so this is, yeah, there are options on this one. So this is one way you can annotate this one. So even there are many other ways. Okay, then okay, and there is also another option, like, let's say, hey, you let's say, yeah, this is our one. So okay, let's say I need to delete one of the graph. Just left click, right click, and give delete this trace. Same goes once more. Right click, delete this trace. So that's it. So now let's say, hey, I need a different graph. I need to plot out one graph have like different curves in different graphs. Just left click this one. So and put add uh, plot plane. When you add plot plane, so you have a different uh, graph here. And now let's say I just click on this current. I can see the hand. I have two different graphs, two different two curves in rather than hand using one two curves in same the curve. Two curves in two different graphs. This, yeah, you can just have to right click this one. You have to right click on the graph. So yeah, that's important. You have to right click on the graph and just click on add plot plane. So this is the option, add plot plane. Okay, now I'm just going to delete one of this one. So yeah, delete this trace. Okay, so yeah, I'm going to delete this plane. Okay, so that deletes this one, so which leaves us with this one. So, and so yeah, this is how you do multiple different curves in different graphs. Now, one of the most important feature that you can do in graphs uh, is to draw graphs for different functions. Like you can make different functions with the voltage, current, and other parameters, and plot a graph directly rather than taking values of voltage, current, and manually plotting a different graph for, let's say, vi, let's say v square I. So like we can make graphs for our v square I. Like we can make different equations and make graphs for that. So for that, let's say I need to make what it has. Let's say I need to make a graph for v out plus 2 v in, v out plus 2 v in. So now I will just click on. So I need to make a graph for v out plus 2 in. So for this case, just so this is v out. So yeah, this is v out, and this is v in. Okay, so I'm going to just delete these two. So it's fine if even if it's there, I can just keep this, but for the sake of understanding, I'm just going to delete this one, these things. So yeah, okay. So that is not really necessary. You can even if there has already a curve in the curve in it, so it is not much of a problem. So like yeah, so let's just right click, click on add traces, and we need v out plus 2 v in. So click on v out plus 2 into v. You can either write the name, because v in is directly here, voltage of v in we have to have. So if you need current, it is current of that particular component, ICIS, current control current source. So if it has a current through voltage control, it should be I of voltage control voltage source, VCVS. I have given the name as VCVS. So similarly I of RS. So now what I need is a voltage of V out plus 2 into voltage of V in. So yeah, here you can see that V in. So let's click on OK, and there you have it. So you have V out plus 2 V in. There are and if you okay, so like similarly you can make number of other functions and plot its graph and yeah. So and also you can see that there are not only these, you have the sine function, you have the log function, and you have the exponential function. There are a number of functions that you can use in the LTSpice, and which you can find in the LTSpice directory. Even you have the logical operations, and yeah, there are a lot of operations you can just see into it. And yeah, there are different equations. You can use the cos function, cos of x function, cos hyperbolic of x function, and the sine inverse function and exponential function. So I'm just going to show you how to use a logarithmic function. There are a number of functions, and now I'm just going to give an example of doing how to do other kind of functions. Yeah, like it's the thing is that you just need to know the correct syntax, and which you can get from the Google sources, or even it has its own directory, LTSpace directory. You can get it from that. Now I'll just show an example of that. So same, the method is same. Just open this. So the same method, just right click, click on add traces. So let's say I need to find what is 20 log mod of voltage of V out. So which is 20 into log. If you just write log, it will be the log with the base E, Euler constant. Okay. Okay, and if you only if you put a 10 with it, you have the natural logarithm which is of base 10. So I need absolute of this one, absolute, here is abs. So and I need V out. Let's say we need V out. Remember to close the bracket, then click on OK. There you have 20 log to the base 10 absolute of V out. So similarly you can make number of other equations, and yeah, you can make a lot of other equation like V square R, Vi, which is for power, and yeah. Okay, so that's it. And one other feature that can come handy while taking, like, the thing is, when you take a printout of these things, most probably the clarity won't be uh, there won't be much clarity in it. So what you can do is, there is an option which enables you to increase the thickness of which will enable like which if you increase the thickness of the one while taking a print out, it becomes more clear. So for that, what you have to do is just go to you can go to tools, you can go to control panel. In control panel, what you can see here is the waveforms. You can see the waveforms. Click on waveforms. So now you can see here there is a data trace width. So I'll just keep it as 4 and just click on OK. You can see the the thickness has been increased. Now if you take a printout of this one, it becomes more clear. So yeah, this will come and yeah, I'm going to just keep the thing in a default manner. So further you can just go back and do the same thing once again. Okay, so this is a yeah, you can change it to 1 and just click on OK. You have the you have it back again. So yeah, so that helps you when you take a printout. Otherwise it is not of much use. But yeah, so when you're taking a printout out, give the adjustment in a right way, that it is uh, visible in a clear manner. So this is about graphs. Okay, so I hope that you guys understood the features that you, some of the features that you can use in while analyzing the graph. So there are a lot of other features which you can check it. So which I have mentioned few which can come in quite handy. Now I'm going to we are going to study or understand about a command called step parameter. Okay, so step parameter. So like yeah, you can see that you can just click on help. Yeah, go to help topic. So you can see the hat here. There are different commands that you can use. Like what is command, all those things I will just say in a minute. So before that, you can see here there is so we can see there is a dot step. So you can click here. So you can read these things. Read these things. So for this I will show you what is a command, what are these things, what are these all about. So yeah, you can see that there is a text option here and there is a spice directive. So if you click on this one, there is a spice directive and there is a command. So yeah, if you just click in this command, okay, so yeah, so this is command, this is spice directive. Spice directives, here you will there are predefined codes for doing different kind of things. So you can understand what that syntax is, what does it do. You can write on it. I mean, you can write on the command and do the required thing. So now we are here, we are going to do look into the working of step parameter. So why do we use that and how is it helpful? So we are going to look into that. Okay. Okay, so yeah, you can see the head here. We are going and we are doing an AC analysis. We are going to do an AC analysis. So let me just run this one. Okay, so if I run this one, you will we'll expect we expect a frequency response, we get a frequency response. Yeah, we get a normal frequency response. Okay, now let's say I need a frequency response for different values of this resistor. One thing that you can do is you can like replace this resistor with different values. Each time you can get a graph, you can note down values, but that is quite difficult. But what you can do is within the same circuit you can plot the graphs of different resistors. That means you can make the resistor as a parameter and you can change the value. You can give, like, you can either give different values that you have to set for resistors, or you can give a range of values with a particular yeah, with a particular time, with a particular gap. Let's say we need 1k, 2k, 3k. So like this is what step parameter does. So there are two cases, usually two cases of step parameter. First case is by directly assigning particular values. Okay, so for that, let's say you need to change different values of the, like, this is not only useful for resistor, it can be used for capacitors, anything. You can make anything has parameter and change its value. So let's say how to change this one for resistor. So left click on the uh, value of the resistor and give a name, put the curly braces and give a name for the resistor. Let's say I'm giving it as RL. So, and close the curly braces and click on OK. Okay, so this is how it becomes. And now we will go to spice directive, and therein we will type dot step param parameter RL. So we'll give the name. This is dot step parameter RL, which is the name of that resistor, and click on list. Let's say I need to give values. I need to give values of 10k, 2k, 5k. Just click on OK and place this one here. Now let's run. So this is dot step para RL, which is the name of this one, and I will click list to give a particular value. I need 10k, 2k, 5k, and I will just run this one. Now you can see that there are three graphs. You can see they had 1, 2, 3 graphs. Each graph correspond to each resistors. So these are frequency responses corresponding for different values of resistors. Yeah. So in order to understand to understand which curves are for which resistor, just keep the cursor in the you can move from one curve to another by just using the arrow key. Here's this if I click on the upper arrow key, it moves up. You can see that, and if you have to go down, you can just click down. So this is how you traverse through different curves. So let's say I need to know how which curve, how does this represent, for which resistor has this curve represents. So for that, just left click this one, so you can see the head cursor 1, RL is equal to 2k. So this is the curve for 2k, and let's say what does this represent, and give the cursor there, left click, so RL equal to 5k. So this way you can you can give multiple different values for, you can make a component as a parameter and give multiple values, and this works same for the capacitors, resistors, and even for the voltage sources, current sources. You can do this one. Okay, just and the step and the steps are same for all. Now let's say you need instead of having particular values, you need to give a range of values. Let's say you need the curves for resistors from 1k to 10k, 10k with a step of 1k. That means that you need 1k, 2k, 3k, 4k, or let's say you need 2k, 4k, 6k. You need like that. Instead of writing it all, you can directly give a command. So I mean, let's just comment this in order to just like if you just put a semicolon here, you can just comment as you can just comment this this one. So that means the hand when just give a semicolon. So when you comment this this one, what happens is that it no longer will be what executed by the LTs by Hayes. It will just stay as a normal comment. So let's say hey, I need as I said, now we are going to change the values of resistor from 2k to let's say 20k in steps of 2k. It is 2k, 4k, 6k, so on and so forth. So for that we need spice directive. It's not common that we need spice directive. So there we'll click dot step param dot step param RL. So let's start from 2k to 10k in steps of 2k. So let's click on OK. Let's run this one. Now you can see that there are a total of 1 2 3 4 5 curves. So you can see if you can just put the cursor in one of this one and left click this one. This is for R equal to 2k, and let's go up. This is for R equal to 10k. So yeah, so this is the syntax of this one. Once again, the syntax of how this one is you must give the initial value, and this is the final value, and here you will give the step with what step. Let's say you need to go from 3k to 9k in steps of 1k, that is 3k, 4k, 5k. You can give 3k here, you can give 9k here, you can give 1k here. But let's say you need to go as 3k, 6k, 9k, 12k, so on and so forth. You just give 3k here, you just give let's say you need 12k here, and just give 3k here. So initial value, final value, and the step that you have to take each time. So this is step parameter, and this will come quite handy when you are analyzing for analyzing each component for different values of each component. Okay, so that is about step parameter. So when you have to use particular thing, you should use dot step parameter with the name and list and just give the values. And when you are using a range of values, you have to give this syntax. And there are also some extra things that you can do, is that you can just read in this dot step parameter sweeps. You can just go through this one, and you can understand what are other things which you can do using dot step parameter. Okay, so that is about dot step parameter.
Okay, so I guess you guys understood how to use the step parameter. Now one other spice directive command that comes quite handy, this command is comes quite handy, and that command is dot measure. So yeah, you can if you need a basic understanding, or you need to know about dot measure, you can go to help topics. You can see here there is a command called dot measure, and from this you can see that there are number of things that you can do using dot measure. And now I'm going to list out some of the things which will come quite handy while using this one. Okay, which will be useful in quite a few more times. So I'm going to discuss a very few of the things that you can do with the dot measure, and you can explore what all other things that you can do either by going through this one, or you can you can itself experiment on this one. Okay, just read this one and just try to do different kind of things. Then now I'll be discussing about some of the basic things that you can do with dot measure spice directive command. Okay, now let's say I need to find the maximum current which is passing through the zone. So for that, let's say I go to the spice directive and I'm going to type in .mes, which is the short .mes dot, don't forget the .mes measure. So, and this is a transient analysis that I am doing. So tran and then like then I'm going to give it name for this one. Let's say I need to give, let's say I'm going to give I1. So this is the name, and then I need to find maximum of current of which one, current control current source, which I have given its name as ICVS, ICIS, current control current source. I have given the name as ICIS. Is this its name? Okay, I'm just clicking on OK. Let's keep it here. Now let's run this one. Okay, so yeah, it will run, and if you go to the if you just click on this one, you will have your graph here. So what we are going to look at, what is the use of dot measure, where can I find the like one way is to like you can directly find this one from the graph if you just find the current through this one. So you can see the current through this one. So if you go to the graphs, let me delete this trees, and you can see that the maximum current is in and around 400 microamps. You can see that it is around 400 microamps. The maximum current, you can see that it's around 394 microampere. So yeah, it's pretty difficult to go through each of the curves, look what the current is. So instead of that, I use dot measure command. Now where can I find the values of this one? For that, you have to go to you can see this one, there is a option called spice error log. Click on spice error log, and there you have it. For each resistor has, you have different maximum values. Yeah, this is 396 microampere, 394 microampere. So for each resistor, like you can also see that this is there is a time step from 0 to 10 second. So within this time, so which is the time that we have given for running the simulation. So within this is what are the maximum values. So these are the maximum values for step 1, which indicates R is equal to 50, step 2 which is R is equal to 1000, step 3 for R is equal to 500, and step 4 which is R is equal to 500. So same thing you can do for the voltage, current, and like even you can use different kind of functions. So I'm not going to show all this, but instead I am just going to show you which all commands that you can do. The way you can you can just understand these commands, you can directly put up in your spice directive, just run the command. So yeah, so these are some of the commands that can come quite handy. So this is dot measure tran v out time. So first you should understand this is the syntax dot measure. So you need a dot measure tran, if it is transient analysis tran, if it is AC analysis, but at some point of time you need to know how to write this one. So anyway, so this is tran, and this is the name that you are giving. So in the previous case, if you can just see view, in previous case I have given the name as I You guys remember that I have given the name as I1, so this is measurement of I1. So yeah, so that is just your name. So this is a name, and this is the command maximum, minimum, RMS. So there are a number of and this is and of what, and this the time. So let's say you need to find the voltage of V out. Yeah, this is the name, the nodal name. So we have already understood how to give names for different nodes. So this is the name of that node, and so like let's say you need to find the voltage at time 2.6 millisecond. So for that you'll just click dot measure trans V out time. There is a name you need to find. That is the syntax for finding. Then voltage V of V out. So that is the name of the node at 2.6 meter. Same thing goes for current and yeah, current through different resistors. Yeah, so these are the codes. You can just check into it. Yeah, even you can use these things: dot measure trans V out. We can find V out when V in is equal to 0.5 time delay. Even you can put a time delay here for that. So you get the following statement: finds the voltage at V out when V in equals 0.5 millivolt, but delay is 1 millisecond before it starts checking. And like let's say if you want to check find the maximum minimum values, you can use these syntaxes: dot measure trans V in max. Just remember that this V in max, V out min, V out max, IR4 max, these are just the names. You can give any names. These are just variables. You can give any names, but these are the syntax. Apart from this, all these are the syntaxes. And even this V in, V out, R4, these are the names which are given to the nodes. When it comes to voltage, it is the name which is given to the nodes, and when it comes to the current, it is the name which is given to the component. If you are using a voltage control voltage source, and let's say you have given the name of that has a let's say V23 or VCVS, something like that. You can give I of VCVS. That will give you that will correspond to the current which is passing through that voltage control voltage source. And if let's say you need the current passing through a resistor which I have named as R4, so yeah, so that is the current I of R4. So you can see that I had these the first three will give you the absolute. I mean absolute in the sense it will give you the maximum throughout the simulation, the maximum values throughout the total simulation. You would have given a particular in transient analysis. You would have given time from let's say 0 second to 10 second starting time, stopping time. So it will give the maximum value within that, or the minimum value, or the as given. And this the last statement gives the maximum value from time, maximum value that is seen for current from time 1 millisecond to 4 milliseconds. So here we can give a range for this one. Yeah, same thing goes for here. So like even here you can find PP means peak to peak value. This is peak to peak value, and this is RMS value. This is RMS value. Yeah, that is peak to peak values from this 1 milli to 4 milli. And yeah, there is a range of max to minimum value within this range, which is PP, and then you have the RMS value. Yeah. So yeah, so these are the different things, and you can also do a number of other things. Peak to peak values, RMS value, and there are maximum values, minimum values, even the average value. So yeah, you know to look in. Yeah, so there is one other thing that so you can use this type of statements: dot measure trans power, like this is the name, and you can use a parameter. So the parameter, this is the name of the parameter in the sense is just a variable. So the name of the variable is power time, and what does it correspond to? It corresponds to V out time into IR 5 times. So we have already given what is V out, yeah, you can see that we have already given what the name, what is V out time, and there has IR 5 times. So and power at that particular time corresponds to V out time into IR 5 time. So that is what. So similarly you can find the gain but the thing is that you give the name for this one, you should have already specified what these things corresponds to. So yeah, there are a lot of other statements. Okay, so these things come quite handy. So yeah, there are a lot of other statements that you can use here. You can find these things in the help topics. You can see that we can do the average, maximum, minimum, pp, find the peak to peak RMS value, or integrating this one. So there are a lot of other options to which you can explore this one. And okay, so that is about dot measure. So yeah, I'll just give you one more example. So here I have used dot measure gain, which is max, which gives the magnitude of v of v out. So that is the maximum value of the magnitude, or you can even use absolute. So this is the anyway magnitude of v of v out, and MES 3 dB value param gain by the square root of 2. That means that the 3 dB value equals the gain, which is the magnitude of v of v out divided by square root of 2. So I need to find the bandwidth value. We dot measure bandwidth when magnitude of v of v out is equal to 3 dB value. So this is I can see that there is no AC written over this one. So because we are doing AC analysis, there is really no need of writing dot AC there. So yeah, it is understood that it is AC by the software. So I have directly written like this. So dot measure VW when magnitude v of v out is equal to 3 dB value. So what does it give you? It gives you the value of the frequency when magnitude of v of v out equal to 3 dB value. So this particular thing is used to find the cutoff frequency. So rather than going to the like if you just run this one, let me close the other graphs. Just into this one. So yeah, you can see that the cutoff is in around this one, but in order to get a accurate value of this one, this is quite helpful. So yeah, you run this one, you have the v out there. Okay, yeah, you will just go to the error log, spice error log. You can see these things. So the bandwidth is at 1.3955 into 10 raised to 8 hertz. So yeah, so this way you can get that you can directly get the value of the gain, which is 94.6 dB, and this is the 3 dB value the value of the gain at the cutoff frequency, and this is your cutoff frequency. This way you can accurately measure cutoff frequency rather than go into graphs and looking through a graph. So this gives an accurate value. So yeah, and dot measure has various other uses which you can explore and which will come quite handy while designing and analyzing different circuits. So that is about dot measure. So in this last section, what we are going to look is how to merge two circuits. Let's say you have made two circuits in two different files, and you need to use both the circuit in a single file. So what can you do? It's very difficult to to build the circuit the same circuit. Like it may be some very complex circuit that you have to merge. So it's very difficult to build it again. So for that, yeah, it's quite easy to merge two circuits here. So just take open two files in the same window. So yeah, so let's say these are the two circuits. Okay, yeah, these are the two circuits. Now just copy any one of the circuits. Yeah, I have selected this window, so I have to copy. You have to copy this one. Sorry. So you have to copy this one. Let's say I copy the whole circuit. Now you can see that I can move this one. So move your cursor. When you reach your left click, so you can see that you can bring this one here. So this way you can directly merge these two. Now you can do you can directly connect these things. You can just click on the wire. You can do the connections. You can do the normal connections. Yeah, you can do the normal connection, and but remember that when you do the merging, you should just give a single it is necessary that you give a single analysis. You should either comment the other what is that simulation command or just give us a single simulation command, and yeah, you can just run this one. You can run this one. So let me delete this one. Let's say close this one. So yeah, so you can see this one, the frequency response of this particular merged circuit. So I hope that you guys understood how to use LTSpice. So one way to have more understanding is to just practice. You just take up some random circuit, just practice it, and go through. There are a lot of other things, other features that is helpful. Yeah, there are a lot of other features that is which you can make use of. So yeah, just explore those things, and keep learning, and have a great and wonderful day.